In today's video, here is a nice problem. It's coming from Turkish Mathematics Olympiad edition 2005-2006. Here is the following information for all m and k as a non-negative integer satisfy this following equation. We have the power of 5 is raised to the m as an exponent plus the power of 7 is raised to the n as an exponent equals k cubed. Okay. In fact, it's a challenge problem because the structure this problem how built, it was in not good condition because they have two primes is raised to the different exponents equals the cubed. Okay, so because we have a different exponent here, we will have a lot of issues here with this. So the big issue with this problem, so how to deal with this exponent m. The issue with this problem, how to connect these three terms to make a factorization clear here. So here is a problem. So you guys, you can give the hand to this problem pre into the solution. By the way, don't forget to hit the subscribe button and support the channel, like, comment, and subscribe. Now let's jump into the solution. If you take a look at this equation, the sum of these two terms is even, which means this one is even. Now let's reduce the equation to the mod 8, which is even. Let's set this one like 2c cubed equals 8c cubed is a congruent to 0 mod 8. So here I get 5 to the m. This one is going to give us minus 1 to the n, because 8 minus number 1 equals 7 is a congruent to 0 mod 8. Okay, so if you go through the chart, the following reminders, we get number 1 5 1 5 1 5. At number 1 we get even terms here. Okay, so by the chart we get reminder number 1 plus minus number 1 to the n is a congruent to 0 mod 8. Okay, what is gonna happen? N must be odd. If n is odd with m is even, this one turns into number 1, this minus number 1 is going to give us 0. Now it's clearly we get the parity of these three integers. So we get k is even, we get n is odd, we get m is even. Okay, it's more clear. Now let's get rid of this one and move on to the next step. Now in this step, let's claim m equals 0. Okay, so I'm not going to prove it now. I'm going to leave the proof at the end because the proof is going to be a longer part. Okay, so now I'm going to take this value and insert it back into this one and solve our equation easily. Okay, k squared plus k plus number 1 like this. Now it's more clear now to solve this equation because we get a power of 7, which means each term of this product must be a power of 7. Okay, so in the other word, GCD of this one equals 1 or 7 because it's a prime, which means the right hand side of this equation also the GCD of this one is going to be number 1 or 7. Okay, let's prove the number 7 as a GCD is going to be out of this possibility. Okay, by the way of contradiction, suppose GCD of k minus number 1, and let's put this one as a capital A, and capital A equals number 7. Okay, so which means each term of this product must be a multiple of 7, which means k minus number 1 equals 7 is multiplied by lambda. Okay, so I'm going to, this one is going to give us lambda equals k equals 7 lambda plus number 1. I'm going to take this value of k and insert it back into this product to see what's the next expression. So I get 7 to the n, which equals k cubed minus number 1 is going to be replaced with this one. 7 is going to be replaced with this one. 1 plus 7 lambda, or is raised to number 3 minus number 1. Let's apply the binomial expansion on this one. So we get 7 to the n, which equals 1 plus 3 choose number 1 is multiplied by 7 lambda plus 3 choose 2 is multiplied by 7 lambda quinary square plus 3 choose 3 is multiplied by 7 lambda cubed minus number 1. So this number 1 and minus number 1 will be cancelled out. I'm going to calculate this one now. I get 7 to the n, which equals 3 choose number 1 is clearly is going to give us 3 is multiplied by 7 lambda plus this one also will be number 3. This one becomes 49 lambda square. This one 3 choose 3 is number 1, is going to give us 7 cubed lambda cubed. Okay, since we get lambda and number 7 in each term, I'm going to take it as a common factor here. So I get 7 lambda factor 3 plus 7 number 7 lambda plus 7 square lambda square. Okay, if I'm going to suppose n is super equal to 2, okay, so I'm going to divide both sides by number 7 because I want to get this one, because if n equals equal to 1, I'm going to cancel one of the 7. When you cancel number 7 out of the 6, you get number 1. I'm going to keep number 7 as a power. If I'm going to put n equals 1, I get this one is turned number 1. Okay, so this one I get lambda factor 3 plus 7 lambda plus 7 square lambda square. Okay, since this one is a power of 7, which means both of these terms must be a power of 7. Okay, so I'm going to reduce this one is to the mod 7. Let's do that. This one is a congruent to 0 mod 7. Okay, because both of terms must be a power of 7 since we have a prime here. Okay, so I'm going to reduce this term to the mod 7. So this one will be 0, this one will be 0, will be left with number 3. Since we get number 7 here and number 7 here, will be 0 because you're reducing to this one to the mod 7. So will be left with number 3 here. So which means 3 is a congruent to 0 mod 7. It's clearly it's a contradiction because we get different reminders. You get 3, which means 7 divided 3, which is impossible. Okay, well, we have contradicted our GCD. Now our GCD cannot be number 7, is going to turn into number 1. So now but remember, GCD equals 1 when we have n is super equal to 2. Okay, so if n equals 1, as I said before, you wouldn't have number 7 here. We cannot apply this theorem. Now we are contradicting our assumption based on this condition. So now we have GCD equals 1 if n is super equal to 2. So I'm going to check the n equals 1 as well because we need to check the case. Okay, when we have a solution. So equals 1, since we get this one equals 1 because you have claimed m equals 0 here. So I get 1 plus 7, which equals 8, equals 2 cubed, which is a solution for this equation. Okay, m equals 0 and n equals 1 with k equals 2. Okay, if you solve this equation based on this condition, GCD equals 1 is taking us to the same result. Okay, let's try that. So since we have GCD of this one equals 1, which means k minus number 1 equals 1. Okay, because you get GCD equals 1 implies k equals 2. K equals 2, which means it's going to take us the same thing. Okay, plus 7 to the n is 7 to the n, which equals 8 after you're replacing k with number 2. So taking this term to the right, I get 7 to the n, which equals 7 to the 1. Exactly, we get n equals 1. It's taking us to the same solution that I have here. Okay, now let's get rid of this stuff and move on to the proof, because I didn't prove this one yet. Okay, it will be a little longer. It will be a nice proof. Okay, so that by the way of contradiction, m not equal to 0, which means m is super equal to 1. Okay, I'm going to reduce the equation to the mod 7 here. So my equation becomes 5 to the m is a congruent to k cubed mod 7, because 7 was cancelled out because of reducing the equation to mod 7. So here is the thing, we are going to make a nice comparison between this k cubed and 5 to the m by doing two charts. Okay, you get number 1, you get 5, we are reducing this one to the mod 7, means I get 6. 5 to the 4th is the same as 5 square is multiplied by 5 square. 5 square it was this one, 4 is multiplied by 4 is 16. 16 we get 2 more than 14, which is the remainder 2. For 5 to the 5th, which is 5 to the 4th is multiplied by 5. 5 to the 4th is already number 2 is multiplied by 5, which is 10. 10 we get 3 more than 7, which is the remainder 3. For 6, just multiplying by 5 here, we get 3 is multiplied by 5 is 15. 15 we get 1 more 7. Okay, let's put this one in different color. Let's put this 6 in different color as well. For number 7, multiplying number 5 here, we get 5. I'm going to leave it as it is. For 5 to the 8, just multiplying this one, 5 is multiplied by 5, which is 25. 25, 4 more than 21. So the remainder number 4. For 9, 20, I get 6 more than 14. Okay, so the remainder 6. For 11, 5 is multiplied by 2, which is 10. 10 is 3 more than 7. The remainder 3. What about 12? 12, simply put number 5 is multiplied by 3, which is 15. Let's name this one as a set number, capital A number 1, which equals 5 to the k, is belongs to this set. 1, 2, and 5, and 6. Let's move on to make the chart for k cubed here. For k cubed, I will have, since we get k cubed, this one, let's put it this one as a x, for example, because we already have k cubed, because to make the difference between this one and this one. Okay, this following reminders, this one always mod 7 as well, because we are in the same statement. Okay, so we get the following reminder: 0, 1, 8, we get 1 more 7, 3, 4, which is 64, 64, 1 more than 63, 5 cubed, which is number 1. For this term, 7 cubed, which is 0, because you get number 7 is divisible by this one. So this set, let's put it as a capital A2 set, which equals k cubed, is belongs to this set, 0, 1, and 6. I will have capital A as a set of this one. A1 intersect A2 is going to give us, look, we will have a shared reminders 1 and 6 only. 1 and 6 are the only reminders which satisfy this statement. Okay, it's not just this one. Moreover, we get number 6 and number 1 as a reminders is situated as at the 3 and 6 and 9 and 12 and 15 and 18 and 21 and so on and so forth. Okay, what does it mean? That means this exponent is a multiple of 3. Okay, based on this information that we have, exponent m is going to be written on the form of 3x. This is the most important information that we have extracted from both sets. We know m equals 3x. Furthermore, m is even. Okay, so which means x also is even. X. So let's get rid of this stuff and move on to the next step, and insert it back into the original equation to see what's given us. So I get 5 to the 3x plus 7 to the n, which equals k cubed. Let's move over this term to the right and 7 to the b. Okay, always what is b is strictly superior than a. Okay, because based on this structure we have built here, because this one is always bigger than this one. Okay, what to do, since we don't know k as a value, we are going to get rid of this one, cancel out k, and going to replace k with its value. Okay, so because it's very important just to show up 5 and 7 only in this equation, it will be more easier to solve. If you put k involved here, you will have a problem. Okay, so this one is going to tell us k equals 7 to the a plus 5 to the x. Let's replace k into this one to see what's the next expression. So I'm going to move over this 7 to the right, so I get here and make 7 to the 2a as a common factor is multiplied by 5 to the x. Factory, it was multiplied by 7 to the a. This term was multiplied by 5 to the x. Okay, which equals 7 to the b minus 7 to the 2a. So if you check with this one, if you check this one, also always 7 to the 2a is still smaller than this one. Why? Because if you take a look at this expression, we get the positive. This one is a positive, So which means the sum of the whole thing equals 7 to the b, which means 7 to the b is always bigger than this one, okay? Which means I'm going to take 7 to the 2a as a common factor here. So it gets 7 to the 2a factor 7 to the b minus 2a minus number 1, okay? Now let's take this one at the top and continue with our proof. Since we get b is bigger than a, which we have a possibility a can take 0, right? Okay, let's take two cases. If a is super equal to 1, okay? I get this term is always divisible by number 7, which means the left hand side of this equation is divisible by number 7 as well. But 3 cannot divide 7 and 5 cannot divide 7 because they are different primes, okay? Which means 7 divides this term, okay? So this one is telling us 7 divides 7 to the a plus 5 to the x. According to the divisibility statement, we get 7 to the a plus 5 to the x is congruent to 0 mod 7, okay? But since 7 divides 7 to the a, but 7 cannot divide 5 to the x. It's clearly it's a contradiction. It's impossible, okay? Which means this case a is super equal to 1 doesn't work. Now let's move on to the next case when we have a equals 0, okay? To go back to the previous equation that we have extracted before, I'm going to replace a with 0. I will be turned into 7 to the a into number 1. So I get the following equation. I get which equals 7 to the a, which equals 1 after replacing a with 0, okay? K equals 1 plus 5 to the x. I'm going to take this value of k and insert it back into the original equation, okay? M is going to be replaced with 3x, as we have proven before. I get 3x, because remember, always we are working m is super equal to 1, plus 7 to the n. Also, 7 to the n, it will be replaced with b, because a was 0, okay? Which equals k cubed is going to be replaced with this one, 1 plus 5 to the x, all is raised to the 3 as a power, okay? I'm going to apply the binomial expansion on this one. So I get here 5 to the 3x plus 7 to the b, okay? Which equals 1 plus, I'm going to use the binomial expansion here. So I get 1, 3 choose 1 is multiplied by 5 to the x, plus 3 choose 2 is multiplied by 5 to the 2x, plus 3 choose 3 is multiplied by 5 to the 3x. I'm going to be left with 5 to the 3x. I'm going to take this 5 to the 3x, I'm going to cancel it out. We'll be left with 7 to the b equals to this stuff. Let's simplify this more. So I get 7 to the b, which equals 1 plus, also this one is going to be 3, is multiplied by 5 to the x, plus 3 is multiplied by 5 to the 2x. Let's take this expression at the top and keep working on it. Now previously working on this equation, after replacing a with 0, I came up with this nice expression here. So notice here, b is always super equal to 1 because b is strictly superior than a, which equals 0, okay? So now we are allowed to reduce the equation to mod 7 since we keep number 7 here, okay? So I get here, these things is a congruent to 0 mod 7. So I get 1 plus 3 is multiplied, 5 is going to be replaced with 7 minus 2. I get minus 2, all is raised to the x, plus 3 is multiplied by minus 2 all to the 2x, which is a congruent to 0 mod 7, okay? Notice here, since m was even by previous argument, which means x also is a even, okay? So if x is a even, this minus sign is going to turn plus sign, okay? So get 1 plus, I'm going to move over this number 1 to the right, so this one is turned to minus 1 here after you move over this one to the right, okay? I'm going to add number 7 here, is going to be 6 because 7 minus number 1. I'm going to move number 6 to the left. I get 6. I'm going to take it as a common factor. I get 6. This one I'm going to extract number 2 here, is multiplied by 3, which is 6. I get here 6. I get 2 to the x minus number 1 plus 2 to the 2x minus number 1. This number 6, after you move it to the right, it was minus number 1. Is a congruent to 0 mod 7. Okay? Since 7 not divides 6, which means 7 divides this one. In the other word, all these things is a congruent to 0 mod 7. In the other word, these two terms is a congruent to 1 mod 7, which means 2 to the x minus number 1 plus 2 to the 2x minus number 1 is a congruent to 1 mod 7. Now also I'm going to add number 7 here. Becomes 8, which equals 2 cubed. Okay, then take this 2 cubed to the left and make it as a common factor, since we have power of 2 in each term here. Okay, so it's more simple. So we get 2 to the 3 factor to the 2 to the x minus 4 plus 2 to the 2x minus 4. After removing this one to the left, becomes also minus number 1 here, is a congruent to 0 mod 7. Okay, now let's do this one more time. Since 7 not divides 8, which means 7 divides this one. In the other word, these two terms is a congruent to 1 mod 7. So I get 2 to the 2x minus number 4. Okay, also I'm going to add number 7 here. Becomes 8, which is 2 to the cubed. I'm going to move over this 2 to the cubed to the left. I will have the following expression. I get the same thing, 2 to the cubed. Now let's take this statement at the top and continue with our proof. Now we'll keep working on this one. This one is not going to stop, because it's going to be repeating again over again, okay, on the same form. Okay, so what's gonna happen? This one always will be 2 to the 3, because after you take a number 1, you add in number 7, you make 2 to the 3 and bring back the terms, and always cancel number 3 out of the exponent. So this one is going to be all the way down to the 2x minus 3 to the 3 minus 3 m prime. Let's put it as a prime here, plus 2 to the 2x minus 3 to the m prime. Okay, minus number 1 is a congruent to 0 mod 7. Okay, this 3m prime is going always bigger than x, because it's running all the way down. It's not gonna stop, because it's going to get us into the negative exponents. Okay, because this is not gonna stop until infinity. Okay, what's gonna happen? This always x fixed, but this one is keep going up. Okay, with this minus sign, negative will win this x. I'm going to replace, to make it more simple, I'm going to replace x with m over 3. Okay, so I get 2 to the 3 factor. So let's set m prime is always bigger than m, because as we said, m is fixed value. This one is keep going up. Okay, I'm going to take negative 3 as a common factor here. So I get minus 3 factor m prime minus m over 3 square. Okay, plus 2 to the minus 3 factor m prime minus 2m over 3 square is a congruent to 1 mod 7. Okay, based on this information that we have extracted, always m prime is bigger than this one. In the other word, this one is always positive, this one is always positive, which means then the exponent become negative. Okay, so this one never ever is going to give us number 1 as a remainder, since we have the exponent negative. Even if you sum them, you are not going with number 1, which means it's a contradiction. Impossible. Okay, what does mean impossible? m super equal to 1 doesn't work, which means m equals 0. Okay, m equals 0 is going to give us the solution that we have found previously. Okay, so by the way, don't forget to hit the subscribe button and support our channel. Thank you for watching. We'll see you next video. Bye.